the long delays, you'd lose too much from relaxation, or there were too big a range of couplings to optimize. But eventually I thought, I got nothing better to try, so I might as well try it. And I did, and it worked. That taught me a lesson. From ever since then, if somebody told me it didn't work, I'd ignore them unless they tell me it'll burn out the probe in the process. So anyhow, I tried it. It worked. Got it structures for about 3 compounds. Wrote one up. Had a poster at the VNC, and I think it was Madison, Wisconsin, I believe, in 1984. But when I got there, I discovered I wasn't the only one that had that idea. It's on the next slide. And there were 4 articles that appeared in 1984, essentially using that idea. I think Klaus Halenga was actually first, if you look at the actual publication dates, but the key one probably was Horst Kessler's Kolach sequence, because he was the only one that actually derived a brand new sequence for detecting long-range correlations instead of just using the modifying het core. And Kolach, of course, stood for correlation by long-range couplings. So I wasn't quite the first, but I was one of the first. And the funny thing is, other than Kessler, who did a couple more work in this area, the others seemed to forget about the idea once they'd proven it worked. But I decided I was going to press ahead with it to see how far I could push it for natural products. Can I have the next slide then? Oh, okay. During the period, just about 4-year period, I actually got 9 publications on 18 different natural products. Most of them were brand new. A few of the other cases, I was just assigning the spectra and confirming the structure was correct. The key one probably is the one that's shown on this slide, and it came from Guyana, where my Toronto colleague Stuart McLean had all sorts of connections, and they were working on a natural products research center there, sent this up. And it had an absolutely bizarre structure. Even now it looks bizarre to me for a natural product, including a spiral ring junction, which is very unusual. And yet using 2D NMR, just long range and correlation, proton and coupling constants and het core, I managed to totally assign it just from NMR, other than a mass spec to confirm the empirical formula. The only thing was, when I sent it off, we sent it off for refereeing. 2 of the 3 referees thought it was great, and the 3rd referee said, no, we must have cheated. We must have determined the crystal structure first, and then use that to assign the NMR spectrum. We actually had attained a crystal structure, but we only did that just before publication, because my co-author, who was the natural products chemist, was a little nervous about this odd structure. And we got it just as we were submitting the paper. And so we convinced the editor, no, we really had done it by NMR. And I think that's the first case of really odd structure done by NMR. But then the next slide shows the other aspect of what I was up to in that period. 2 particular sequences that I think became fairly well known, and I'll be talking about them. What I called X-core-FE for X-nucleus correlation in a fixed evolution time. And the other was flock, which Martin suggests the name. It had 3 bird pulses, so it must be a flock of birds. Total, there were 7 papers published with different new pulse sequences during that time period by my group. And including the first papers that could, pulse sequences that could distinguish between 2 and 3 bond correlations, which, as I said, was a sort of problem. Okay, the next slide. All of the work I did was based on these so-called bilinear rotation decoupler pulses, or bird pulses to abbreviate them, which were actually developed by Alex Pine's group. One of his few times I think he did anything out in that high resolution area. And they were selective proton decoupling pulses. And as they say, they were a 90, 180, 90 proton with a 1/2J delay, if I recall correctly, and a 180 carbon simultaneously with the proton. And depending on the relative phases of the different proton pulses, you could do one of 2 things. It would always be a 180 for the carbon, as illustrated in this cartoon. It flipped that But the proton depended on the phases of the pulses. It could do one of two things. It could either flip the protons bonded to C12, or it could flip the protons bonded to C13. As I think you can see, that gave you a lot of leeway for playing all sorts of what Ray Freeman used to call spin gymnastics, to play with both with existing pulse sequences and new ones. Okay, my next slide then. The first one I decided to work on was, I thought I could improve Coloc. Now, sorry, I should have had this slide showing Coloc. This is my version of Coloc, which I then called XCore FE, but for the purpose of this talk, I renamed this and some other sequences as in sort of modern terms. This follows a different sequence by Gary Martin using HMBC. It's an appropriate name because it's Coloc designed to distinguish between 2 and 3 bond correlations, which Coloc itself couldn't do. Coloc actually, in place of the bird pulse, the first bird pulse, had just a pair of 180s. It didn't have the second bird pulse at all during the refocusing delay after polarization transfer. And it was a constant time sequence. It generated the information by having the pair of 180s move through the time period. For some reason, I got the time period reversed in this slide. I can't remember whether that was because of some instrument artifact or whether I just drew the slide up wrong, but it really normally would start in the pair pulses would normally start on the left-hand side and move across to the polarization transfer. And because it was constant time and all the spins were by the 180, there was no refocusing of the proton-proton coupling constant. So you got a spectrum with full decoupling. So it was a sort of a pure shift spectrum at that point. They were all singlets. But there were problems with it when I analyzed it, and I was Kessler himself had commented on the problems of finding the optimum parameters. The total time delay before polarization transfer was based on long-range couplings and typically be 50 to 70 milliseconds. But if you got slight changes in that, or slight, depending on the couplings and the chemical shifts, some peaks would not appear that you'd expect. And I figured by inserting the 2 different bird pulses, you could at least minimize that problem, particularly the second one, avoided what Gary Martin called one-bond modulation, which would cause you to lose peaks sometimes. But the first bird pulse had another very important thing, which is illustrated with the cartoon down below. When you had a selective bird pulse, these were indirect bird pulses, it would be refocusing. Whoops, my slide just, oh, there we go. It would be refocus. Sorry, back again. I had a glitch on my computer. Okay, if you look at the bottom thing, you were refocusing different pulses, but the 3-bond proton-proton, which is usually the largest coupling, was the one that would be refocused by the variably, in a variable sense, because as you move the pulse behind, it would be refocusing it different ways and it would modulate it. So you'd see the effective modulation of this large 3-bond coupling, but the 4-bond coupling was so small that even though it was modulated, it wouldn't have any effect on the spectrum noticeable, because the effect would be less than the line width. And the 3-bond coupling, of course, the proton-proton is associated with the 2-bond carbon-hydrogen correlation, and the 4-bond is with the 3-bond carbon-hydrogen. So this, taking advantage of the fact that you were reintroducing coupling, which was specifically associated with the 2-bond coupling, allowed you to distinguish between 2-bond and 3-bond, as illustrated on the next slide. Now, this shows a very simple test molecule we used, and I'll focus just on the top slide, which I'm having, it's not showing up very clearly on mine, but I think this was a correlation with C5 carbon, which should show correlations with C4 and C3. Proton 4 and proton 3, sorry. Proton 3 corresponds to a 4-bond proton-proton coupling to the methyl. Proton 4 is a 3-bond. So protons, the coupling between proton 4 and carbon 5 shows up as a quartet. It's modulated by the coupling between 4 and 5, whereas the small coupling between 3 and 5 doesn't affect it in any significant way. So you had a way of distinguishing 2-bond and 3-bond correlations from that. I apologize for the lousy quality of the spectra. That was actually run on an XL200 with a 10 millimeter probe, and I think about a 35 microsecond proton pulse. So there were problems with running it that way. Fortunately, soon after we got access to a 400 and then later 500, where I could make much better spectra. Now, at the same time, a thought had occurred to me that Coloc is, as I say, a pure shift type spectrum. It would be nice if we could convert it into a 1-bond correlation spectrum. Now, one way you could do that would just by shortening the time down to make the delay 1/2J for 1 bond, but that would be about 3-4 milliseconds, and you would get lousy proton resolution. So, and thought about a little bit, but if you could go up to 3/2J, you'd be up around 10 or 12 milliseconds, and that gave maybe 25 hertz resolution. So we tried to actually publish it, what you might call ASAP HETCOR, because you could get a crummy spectrum very quickly. But I really want to do better. I wanted to get down maybe 4 hertz. And then all I was doing to develop these pulse sequences was sitting there with a pencil and a notepad and drawing vector diagrams and seeing how I could manipulate the spins to achieve what I wanted. And when I figured out for the getting a pure shift core types is shown on the next slide. This was essentially Coloc again with the pair 180s moving through, but I put it in a bird pulse right almost in the middle. And the idea of that, and this was an indirect bird pulse, the idea was that it would get everything in the order I wanted at the end of the period. I wanted about a 70 to 80 millisecond times fixed constant time, because that would give about a 4 hertz resolution, I figured. And what the bird pulse just set everything up just nicely. I'll just look at one thing, is that the total time before the pair 180s was tau, big T. The time afterwards was T minus tau. And so that it refocused it, but not quite all the way. It left it at 1/tau, which is 1/2J. So it was set up perfectly for the antiphase proton vectors for the polarization transfer. And in various ways, both with the bird pulse and the time, the various vicinal and general vicinal couplings and general couplings as well were all set up right. But there was only one problem, is that I wanted to use the whole time period, but as the pair 180s moved through the first time period, it would bump into the 9-degree pulse. So what do you do about that? How do you get a pulse to leapfrog over 3 other pulses and come out the other side? Well, fortunately, that was actually very easy with variant software. I'm told that nobody else could run it on other spectrometers because they didn't have that option. But we had a conditional statement was allowed in any pulse sequence. If something, do this, otherwise do that. And so what I just put in is small t1/2 is less than big T, run the first sequence. If it's larger, run the second sequence. The 2 sequences compile together and run sequentially without any glitch or anything. It's just one smooth whole experiment with 2 different pulse sequences, which is, as I say, at that point at least, was unique to Varian. And to show how it worked is also the next slide. This is a pure shift HETCOR spectrum. Sorry that the dots are pretty light, but as you see, it was very high resolution, everything nicely resolved. And interestingly, if you look at, across the top, this is a projection spectrum of the 2D spectrum. What you have is a pure shift 1H spectrum. And you'll note, unlike the pure shift HSQC or the Bax version of Bird decoupled HETCOR, even the methylenes are singlets and very quite well resolved. So I'd like to claim to have been the first pulse sequence that could produce a pure shift 1H spectrum long before Gareth Morris's. But of course, Richard Ernst B2 back in 1976, I think, with its homonuclear J resolved experiment, we could also produce a pure shift 1H spectrum, although it was rarely used for that purpose. Okay, well, I achieved that, but then it occurred to me it would be nice to sometimes one bond carbon hydrogen coupling constants are useful information. If you could somehow get that back in the spectrum, that would be sometimes valuable in stereochemistry. This is an alkaloid where the lone pair of nitrogen tends to affect coupling constant particularly. I thought about it. Well, one obvious way to do it would be just to turn the decoupler off during the acquisition. You'd get the coupling would appear along F2, but that got to be messy and it wasn't very elegant. I wanted to find a clever way of doing it, so came up with the pulse sequence in the next slide. Again, just using pencil and paper design. Never heard of product operator formulism at that stage. What I started doing was just removing the carbon pulse from the carbon-proton pair. It was the same modified Coloc sequence with same bird pulse. I just left the carbon pulse off on the grounds that as the proton 180 moved through, the one-bond carbon-hydrogen would be modulated and would show up along F1. It turned out there was a minor glitch. You really needed to, because of the way it functioned, you need to introduce another short refocusing element to get it working perfectly so it didn't have some discontinuity. And I again figuring out various alternatives. What I came up with is if I put in second 180 at the end of this bird pulse in one way, or when I did it the other way through in the other half of it, I put the 180 at the beginning of the bird pulse. When I did that, again, using this if-else statement, on the next slide, it shows the results. And again, you have everything, nice doublets for each proton with a 4 Hertz resolution and with enough zero filling and so on. I found you could estimate coupling constants to probably a little better than 1 Hertz at least. Mind you, that wouldn't be good enough. In principle, you could use this for measuring residual dipolar couplings, for example, but I don't think wouldn't be quite accurate enough for that. But it was pretty good under the circumstances, I think, for a carbon-detected sequence. And the thing that at the top is a slice through one of the carbons, showing that when there were two different methylenes, you could, even with partially overlapping signals, you could resolve them enough to see the coupling constant. So that was another experiment. But then I decided it was time to go back to long-range correlations and see if I could come up with a different way. As I mentioned, these fixed time or constant time sequences were temperamental to find optimum conditions, and simple het core was better, but I thought you could still do better with simple het core as well, and that's on the next slide. And that's where the famous flock name came in. It actually started out, the first time I tried it was only with 2 bird pulses. It was essentially the same idea as what I've been doing with Coloc. But this time the bird pulses were just before and just after the polarization transfer in these refocusing periods. One thing they would do is wipe out one bond coupling correlations pretty effectively and remove what Gary Martin called one bond modulation. But in addition, if I wanted, and in fact I did it later, it allowed you, having those refocusing pulses and those delays, allowed you to convert it to a phase sensitive spectrum if you wanted instead of absolute value. So tried that, it worked, but then it occurred to me, well, 2 birds fun, why not try 3? And then as Gary said, I had a flock of birds. And when I analyzed, I realized there were actually some advantages to doing it. It was a little more one bond suppression particularly, but more interesting thing is it worked just the reverse of Coloc. This was the first bird pulse was a direct bird pulse in this case. The other two, as similar in my Coloc modification, were indirect bird pulses. what happened was that you would have a refocusing of the proton couplings between protons on C12 and protons on C13 by this bird pulse. And of course, the largest couplings again are the vicinal couplings. So what would happen is, whereas in Kolak you reintroduced the coupling, in flock you eliminated that large coupling. There were a couple potential advantages. One obvious one, by simplifying the multiplets, it'd be narrower, taller, and therefore your signal noise would go up. But also, in principle at least, by comparing the the flock cross sections with the original proton spectrum, you might be able to see enough of a difference to determine whether it was a 2 or 3 bond correlation. Now that turned out to be rarely practical because of the complexities, but nevertheless, it worked really nicely. It was probably the cleanest pulse sequence I've ever worked with. It just did not produce artifacts. And it also turned out the bird pulses really helped. It was, if you compared it with het core without the bird pulses, it was at least twice as sensitive, sometimes even more, somewhat more sensitive as version 1. Now, but still I wanted to be able to use version 1 on occasion. And of course, again, they could be compiled as a single experiment, a single pulse sequence with a flag that told you which version you want to run. And since 2 birds was no longer a flock, the flag I came up with to remove it was flock off, yes or no. So if you put flock off equals yes, you went back to running sequence 1. Still, I think that, again, that was one of the beautiful things of variant sequence that showed up in many other ways. For example, in the when you were doing spectral editing with HSQC, you didn't have to run a different pulse sequence if you wanted to run a different version, or if you wanted to run it coupled instead decoupled, you didn't have to find a different pulse sequence. My Brooker colleagues would get frustrated going through the alphabet soup of Brooker pulse sequences, trying to find ways of doing things like that where I could do them just by clicking on a flag, which I really appreciated. Okay, let's see how that worked. Now, next slide. Okay, I'm not sure how well this is showing up. It's not showing up very well on my screen. But what it was a spectrum of, was essentially almost a segment of natural rubber. It's called a polyprenol. It had 12 isoprene units in a row with sometimes cis and sometimes trans forms. As I think it behaved like natural rubber. It was very flexible. It gave very high resolution spectra, but as you can imagine, it gave extremely crowded spectra. But one advantage of doing carbon detection versus proton detection is that you're using the carbon axis as the detection axis, and you can acquire a lot of points if you want, especially since you're doing proton decoupling, which doesn't heat as much as carbon decoupling. So you get very good carbon resolution. And because the proton width was narrower, you could get good proton resolution. And by the time I actually ran this, I was already starting to use linear prediction to improve it even more. Now, whether you can see this slide, I can't see it very well, but what it showed was there were 6 carbons in a 0.12 part per million range, 6 methyl protons within a 0.15 part per million range, or I think 12 with 15 hertz and 7 hertz, and yet they were all resolved by the flock spectrum and showed what ultra high resolution you get. So it still has some value. People have used it occasionally when they need really high resolution on both axes. Now, then it's suddenly, a little while later, I had another student who was looking for him something to do so he could get his degree. And I came up with another idea, which is shown on the next slide. And this was, what occurred to me is that I had these 2 versions of flock, which are labeled 1 and 2, and they weren't much different. They were both basically flock type sequences. And it occurred to me what I could do is run half as many transients on one and and the same number, again, rather than doing, say, 32 transients on flock. I could run 16 on each version. I could do them in interleaved even, and then at the end I could add them, and I get the same, essentially a flock spectrum in the same time, with the free bonus that I could subtract one from the other, and because the full flock gave decoupling of the, particularly of the vicinal coupling, and the one without the bird pulse did not. So you get a different spectrum, which should show only those peaks that had differences, which would correspond to the two-bond correlations. So this is another way of, better than just flock alone, of distinguishing the two-bond correlations. The only trouble was when I tried it, it wasn't a clean separation. And what I decided the problem was is I was leaving out the time interval associated with the bird pulse in the second version, so things weren't matching up quite well. So I decided what I needed to do was find a pulse sequence element that took the same amount of time as a bird pulse, but did no decoupling. And that's on the next slide. And that was what I called a Dodo Pulse, for do-nothing decoupler pulse. But I named it that primarily because it was an extinct bird pulse, or a dead bird pulse. And the most famous extinct bird pulse is the Dodo Bird, you know, the old expression, dead as a dodo. And what it did was, by, you know, the bird pulses relied on one bond carbon evolution during those delay periods tau. But if you put a 180 in the middle of each sequence, there was no evolution and therefore no decoupling. It acted as 0-degree pulse for all protons and a 180-degree pulse for all carbons. And to show on the next slide, hopefully this one shows up better. They're coming weak on my screen, but what it is, I hope you can see this. It was, the one on the right is the one with the different spectrum, which I called CH2BC because it's carbon-hydrogen two-bond correlation. And what it showed, hopefully you can see it, I apologize for the quality of these spectra, that it totally wiped out the three-bond correlations. Even at very high signal to noise, you could not see any three-bond correlation. Even very strong ones from methyl groups were totally wiped out. So it worked very effectively in doing what I wanted, to giving you a two-bond only correlation spectrum, which exactly mimics, of course, the H2BC spectrum that Sorensen, this sequence that Sorensen developed a number of years later. So we had a beautiful way of distinguishing two-bond correlations from others. There's only one catch, which actually I had to blow up the scale on the right-hand side by, I think, about a factor of 4, because the decoupler difference peaks were relatively weak. And what I found when I tried to use it on a real system, you know, realistic molecule with complex proton multiplets, the change in the multiplet structure from the decoupling just wasn't enough to give a very strong peak. And since you were working with a carbon detected signal, which was limited signal noise to begin with, you really could not detect them. So the hopeful extra gain was not really achieved. So I would classify this under a category of pulse sequences, which I'm not the only one that have written them, that were extremely clever and not much used in practical terms. So I don't think that was ever much used, whereas the flock sequence is still occasionally used and is still useful. So that's sort of to sum up what I talked about in these 5 pulse sequences on that next slide. That here I put down the pulse sequences I developed. Here I put down what I would say are the equivalent pulse sequences. I mean equivalent, and they achieve exactly similar sort of results. I apologize, there's some error in this slide. It says F1 decoupled. It should be F1 coupled. You have pure, but we have the 2J, 3J Coloc, which mimics Gary Martin's 2J, 3J HMBC. Of course, pure shift het core, which is better in some ways than pure shift HSQC. And F1 coupled pure shift het core is similar to the F1 coupled Bird HSQC, which I think I believe it was Tio Pere and Roberto Gil were working on that or something similar as a way of getting RDCs off F1 axis rather than F2. Then, of course, Flock relates to HMBC, and CH2BC relates to H2BC. Of course, they're different sequences, but they achieve the same results. The main difference, of course, is they were carbon detected when I was doing proton detected here. But I think what it shows is, with a little bit of imagination, as I say, nothing but a pencil and paper. Of course, it helped that they were single quantum experiments. If they were multiple quantum, I don't think I could have got away quite that easily with pulse sequence design. But nevertheless, just by playing fun, having fun, playing games with how to manipulate the spins by using bird pulses, I managed to come up with, as I say, the early equivalent of modern day pulse sequences. So when I look back, I'm still sort of amused and satisfied by what I managed to accomplish, even if they're no longer hardly ever used, because why would anybody run carbon detected when they can run proton detected? At least until maybe if you had a carbon detected optimized cryoprobe, you might think about them. Otherwise, it won't bother. But nevertheless, it was a lot of fun, which is the main message I wanted to get across. So the next slide, which I think is this summarizes the people that were involved directly at the experiments I talked about. Raul Enriquez was my Mexican colleague, who I've collaborated with on many of the pulse sequences. Stuart McLean is a Toronto colleague who's had all sorts of connections in the Caribbean. So I got samples from originally Guyana, then all three from Trinidad, Barbados, and Jamaica. Don Hughes was helping to run the NMR facility at the time. Marion Perpick was a student through that period who was involved in most of the pulse sequence design. Jiping Yang was involved in the final, the Dodo Pulse one. As I say, I've learned a lot out of 61 years in NMR. Hopefully I haven't forgotten too much in the process. I still seem to remember a good part of it. And I'm still trying to keep active. And the reason I've kept active so long is because it is fun. And I hope other people continue to find it fun too, because I certainly enjoyed it. So thank you for your attention. That's all I have to say tonight, I think. Okay. 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 Thank you for the opportunity.
Recording